A laser beam is a system of engineered electromagnetic coherence, aligning photons in both space and time. In industrial manufacturing, that coherence dictates the absolute limits of what we can physically build. A thermal cutting system relies on this exact alignment to achieve precise tolerances of plus or minus 0.1 millimeters. Keeping the beam this concentrated prevents thermal bleed. It strictly minimizes the heat-affected zone, ensuring the surrounding metal's original microstructure stays completely intact. In medical applications, the mechanics of the beam are tuned for biological tissue rather than steel. Here, a laser's specific wavelength dictates exactly how its photons interact with cells. The Lambert-Beer law equation, I of z equals I sub o e to the negative alpha z, models the exponential decay of light penetrating a surface. Changing the absorption coefficient, alpha, dramatically shifts the laser's depth of impact, determining whether a beam ablates a surface lesion or penetrates deeper to coagulate a blood vessel. Achieving this level of macroscopic precision requires us to subvert the laws of thermodynamics at the subatomic level. This diagram maps the three essential hardware components required to generate a beam: an external energy pump, an active gain medium housed in a quartz glass tube, and an optical resonator made of two parallel concave mirrors. When the pump injects energy into the gain medium, the atoms absorb that energy and become excited, but they do not hold that state. Within a few nanoseconds, they release the energy as random photons and drop back down to their lowest energy level. This graph models the Boltzmann distribution. Under normal equilibrium conditions, the ground state population is vastly larger than the excited state. Because ground state atoms outnumber excited atoms, stray photons are immediately absorbed. This rapid absorption prevents a continuous beam of light from forming. The thermodynamic barrier is bypassed through metastable states. These are specific energy tiers where excited electrons temporarily stall. Instead of decaying in a nanosecond, an atom waits on the shelf for up to a millisecond, 1,000,000 times longer than a standard excited state. Because the atoms linger on this upper shelf, they begin to accumulate. Eventually, the number of excited atoms suspended in the metastable state surpasses the number of atoms sitting at the ground state. This non-equilibrium condition is called population inversion. It is the mandatory requirement for generating a laser beam. The helium-neon laser, developed in 1961, was the first continuous wave gas laser to achieve this. It operates on a strict 10:1 volume ratio of helium to neon gas. The counterintuitive engineering behind this system is that we do not pump the actual lasing gas, the neon, directly. In this energy level diagram, the power supply targets helium. The current causes helium to jump to the highly excited 2,1s and 2,3s states. These energetic atoms physically collide with ground state neon atoms. Because helium states align perfectly with neon's metastable states, energy transfers smoothly. There is a strict division of labor here. The helium acts entirely as an energy carrier. It absorbs the electrical shock, holds the charge, and passes it to the neon, which serves as the active gain medium. Without this engineered two-step resonant energy transfer, the neon atoms would rapidly decay, and population inversion would be physically impossible. Once population inversion is achieved in the neon gas, atoms begin dropping from their metastable states. They release spontaneous photons, which then strike other excited neon atoms, triggering a massive chain reaction of stimulated emission. This stimulated emission bounces back and forth between the two mirrors in the optical resonator. Each pass multiplies the number of coherent photons traveling perfectly in phase. Inside the active neon atoms, dropping from the 3s and 2s metastable levels to the 2p level generates distinct wavelengths. Two drops produce invisible infrared waves, measuring 3.39 and 1.15 micrometers. The third transition produces a visible red wave at exactly 632.8 nanometers. To isolate that red beam, the system relies on physical filtration. The quartz glass of the tube itself is naturally opaque to the weaker 3.39 and 1.15 micrometer infrared waves, absorbing them entirely into the tube walls. The remaining 632.8 nanometer light reaches Brewster's angle windows placed at the ends of the tube. These specifically angled windows cut the perpendicular components of the light, allowing only perfectly polarized waves to exit through the partially silvered mirror. The pure red beam is a highly sculpted output. It is generated by quantum excitation and refined by mechanically stripping away the unwanted atomic frequencies dictated by neon structure. That perfectly polarized 632.8 nanometer beam exits the optical cavity, crossing from the quantum scale back into the macroscopic world. The helium-neon resonant transfer creates a highly stable, continuous wave, but it generates very low power, typically well below 250 milliwatts. This limits its utility to precise applications where thermal damage must be avoided, such as diagnostic instruments or low-level laser therapy in medical clinics. If the goal is heavy industrial manufacturing, you cannot simply turn up the electrical current on a helium-neon tube to cut steel. This chart compares different laser systems. To change the macroscopic physical force of a beam, engineers must completely swap the gain medium to access entirely different metastable states. A carbon dioxide laser operates at a 10.6 micrometer wavelength. This specific atomic structure places it firmly in the thermal category, generating enough raw power to rapidly vaporize metal, vastly outperforming helium-neon. The choice of that gain medium traces directly back to the Lambert-Beer law. The absorption coefficient of the selected wavelength dictates whether the beam will cleanly ablate a tissue layer or minimize the heat-affected zone in a steel plate. A laser beam bridges these physical disciplines. Every macroscopic application, from the geometry of an industrial cut to the precise cellular depth of a surgical incision, is a direct engineered manifestation of quantum mechanical transitions.